This is problem set number 4, problem 6. A cylinder contains oxygen at a pressure of 2 atm. The volume is 4 liters and the temperature is 300 Kelvin. Assume that the oxygen may be treated as an ideal gas. The oxygen is carried through the following processes. It is heated at a constant pressure from the initial state in state 1 to state 2, which has a temperature of 450 Kelvin. It is then cooled at constant volume to 250 Kelvin, which is the volume at state 3. And then it's compressed at constant temperature to a volume of 4 liters, which is the volume in state 4. Then it's heated at constant volume to 300 Kelvin, which takes the system back to state 1. Part A show these 4 processes in a PV diagram, giving the numerical values of P and V in each of the 4 states. Okay, I could do that. First, let's write down our givens. So we have a cylinder containing oxygen, which is a O2, right? That's a diatomic gas. And we're given that the pressure, initial pressure, P1 is equal to 2 atm. V1 is equal to 4 liters. And T1 is equal to 300 Kelvin. Okay? And it's stated that we treat it as an ideal gas. Okay? Okay, so let's write down the 4 processes that we have, okay? So in part 1, which is from state 1 to 2, we have constant pressure, so it's isobaric, right? That just means constant pressure. And it tells us that T2 is equal to 450 Kelvin. And the second process that takes us from state 2 to state 3 tells us that it's cooled at constant volume, so it's isochoric or constant volume process. All right, and it says that the temperature at state 3 is equal to 250 Kelvin. All right, and the third process, which takes us from state 3 to state 4, is compressed at constant temperature, so it's isothermic or isothermal. And it tells us that, it tells us that the temperature at state 4 is, the volume at state 4 is 4 liters. Okay, and the final process number 4, that takes us from state 4 all the way back to state 1, right? And it's isochoric because it is heated at a constant volume, so isochoric. And it takes us back to T1, right? Which we already know T1 is 300K. All right. Awesome. So before we write the PV diagram, we have to know what is P1, V1, P2, V2, P3, V3, and P4, V4. Okay? And so I'll just put a little note here for P1, P2, P1, V1, P2, V2, P3, V3, P4, and V4, okay? So I need to know these values in order for me to draw the PV diagram. So far, what do I already know? Do I have P1? I do have P1. I have V1, that's given. What else is given? V4 is also given, right? That's 4 liters. And I think that's it so far. Okay, so I'll have to figure out the rest. So I'll just put this right here. This is what I need to know to draw my PV diagram. All right, so let's start in part A. I'm going to start with process 1 to 2. Again, that's isobaric, right? Or constant pressure. So if I use my ideal gas law, PV equals nRT, for an isobaric process, P is constant, N is constant, and R is constant. So I'll have V1 over T1 will be equal to V2 over T2, right? All right, and I know my temperature 2, I know my temperature at state 1, my temperature at state 2, and my volume at state 1. So I can easily find my volume at my V2, right? So my volume at state 1, again, is 4 liters. My temperature at state 1 is 300 Kelvin. I need to find V2, but I do know my temperature at state 2, which is 450 Kelvin, right? So then I could do algebra and solve for V2. I would find that my V2 is equal to 6 liters, okay? So now I know V2. Now I need to solve for P2. Actually, I don't, because this is isobaric, right? It's an isobaric process from state 1 to state 2. So whatever is my pressure at state 1 is also my pressure at state 2. So P1 is equal to P2. So isobaric, or constant pressure. Therefore, P1 equals P2, which is equal to 2 ATM. So I know P2. Awesome, we're getting closer. So now let's look at state 2 to state 3, which is an isochoric process. Okay, I'll just move that down a little bit. All right. So again, I'm going to use ideal gas law, which is PV equals nRT. And this time isochoric, what is constant? Isochoric means constant volume process, right? So V is constant, N is constant, and R is constant. Therefore, P2, since we're going from state 2 to state 3, P2 over T2 will be equal to P3 over T3, right? And we know our P2. P2 is 2 ATM. T2 was given to us 450 Kelvin. P3, we don't know. We'll try to find that. And T3, it was given also at 250 Kelvin. Again, do algebra and solve for P3. Cancel out the units. And you would find P3 is equal to 1.11 ATM. Okay? So now we know P3. Let's check that off our list. What is V3? Well, we don't need to solve for that because remember the process from state 2 to state 3 is an isochoric process, which means constant volume. Therefore, V2 will be equal to V3, which is equal to 6 liters, right? So now we know V3 as well. So it looks like all we need to solve for now is the pressure at state 4. Then we will be able to draw our PV diagram. So, from state 3 to state 4, we have an isothermal process. Isothermal process, right? Okay. We already know V4 is 4 liters, that's given. So let's solve for P4. Again, I'll use the ideal gas law, PV equals nRT. Right? Now what is constant in an isothermal process? So what's constant from state 3 to state 4? Isothermal means constant temperature, so temperature is going to be constant. R and N are also constant, right? So as a result, we'll say P3 and V3 is equal to P4 times V4, right? Because since N, R, T are constant on the right side, from state 3 to state 4, P3 and V3 is equal to nRT, which is constant. P4 and V4 is also equal to nRT, which is constant. Therefore, P3, V3 is equal to P4, V4. Right? Okay. So moving forward, let's plug in P3, that's 1.11 ATM. V3, that's 6.0 liters. P4, we're trying to solve for that. V4 was given to us, that was 4 liters. Okay. So, use algebra and plug it in the calculator, you would find that P4 is equal to 1.67 ATM. Okay, so now we have P4. And if we look at our lists, we need to draw the PV diagram. We have everything. So let's draw the PV diagram. All right. Okay, I'm going to move this a little bit. So this is my volume, this is my pressure in ATM, that's the units, and my volume will be in liters. Okay, so P1, V1, pressure at state 1 is 2 ATM, right? So let's say this is 2 ATM. And my volume at state 1 is 4 liters. Let's say this is 4 liters. Okay. So this will be my state 1. Pressure at state 2 is also 2 ATM. So it's isobaric, it doesn't change, constant pressure. My volume, however, is 6 liters. So we'll put that right here. Going up. So this is state 2. All right. Then state 3, we have the volume is 6 and the pressure is 1.1. So we'll go somewhere like, I guess 1.1 would be somewhere in here. So 1.11 ATM with a volume of 6 liters, so that's right about there. So that's state 3. State 4, the volume is given to us, right? That's 4 liters. And the pressure we found was 1.67. So I guess somewhere here. Oh, oops. So somewhere here, 1.67. same volume, 4 liters. And that is state 4. So let's draw that. We have an isobaric process from state 1 to state 2. So constant pressure. Isochoric process or constant volume from state 2 to state 3. So constant volume, that's a straight line. Then we have an isothermal process from state 3 to state 4. So that would look like that. Then we have an isochoric process from state 4 to state 1. So that would look like that. Okay, and that is our answer for part A. That's the PV diagram. All right, moving on to part B. Calculate Q or heat transfer and W or work for each of the 4 processes. Okay, I could do that. So part B, find Q and W for each process. Okay, let's start with process 1, or this process from state 1 to state 2, which again is isobaric, right? Constant pressure. So what can we say about an isobaric process? The work is going to be the area underneath this curve, right? And it's a straight line, so we just need this area of the rectangle, or the pressure times change in volume, right? The constant pressure times change in volume. Okay. So work from state 1 to state 2 is equal to the pressure times the change in volume. But you know what? I don't want to use if I do that, it would be what, 2 ATM multiplied by 6 liters minus 4 liters, which is 2 liters. So it would be 2 ATM times 2 liters, which is not the units I want for work. So I'm going to do a little trick, okay? So I'm going to use the ideal gas law, PV equals nRT. I'm going to find the delta of this, right? And the delta works like a derivative in the sense that you could bring out the constants, okay? So I've got delta PV is equal to delta nRT. In an isobaric process, which is what we're dealing with, we have constant pressure. So I'm going to take pressure out since it's a constant. So I get P delta V is equal to, my constants are N and R on the right side of the equation. So I'll bring those out. NR delta T, right? Okay. So now that I have that, I could say that work from state 1 to state 2 is equal to P delta V or NR delta T, right? I just brought this down here, but instead of P delta V, I used NR delta T since they're equivalent, okay? So I'm going to plug my values in. Great, I don't know, we weren't given the number of moles either, okay? So we'll have to do a side mission to find the number of moles. And whatever side missions we do, I'm going to use brown ink, okay? So side mission to find the number of moles, I will again use, so side mission number 1. Okay. I'm going to use the ideal gas law, PV equals nRT, to find N, because I know in state 1 we were given the pressure, the volume, and the temperature. So I have everything but the number of moles, right? Because R is a constant, and we should know that R is equal to either 8.31 joules per mole times Kelvin, or it's equal to 0.08206 liters times ATM over mole times Kelvin, okay? And again, these two are the same thing. They're equal, they both equal R. They just have different units. One has joules in the numerator, the other one has liters times ATM in the numerator. So they're both correct, and you can choose whichever value you want to use, whether it's this value or this value, based on the problem you have and based on what units you want to cancel out. Okay? So in this case, I have P1, which is, or first I'll find N, right? Because that's what I'm trying to find. N is equal to P1 V1 over R T1, right? And we just said that we know what the value for P1 is, or that was given to us, right? That's 2 ATM. The value for V1 is 4 liters. R is, I'm going to use this version of R because I have liters and I have ATM in my numerator, and that's what I want to cancel out. Okay, so it's just pick R based on what units you want to cancel out. So I'm going to use 0.08206 liters times ATM over mole times Kelvin. And for temperature, what is my temperature at state 1? It's given as 300 Kelvin, right? So then we know that N, if you plug that in your calculator, cancel out the units, N will equal 0.325 moles. Okay? Okay, so we've successfully completed side mission number 1. Let's go back to our problem. So W work from state 1 to state 2 is equal to N, which is 0.325 moles, times R. This time I'm going to have mole and Kelvin, right? Mole for N and delta T will be Kelvin, so I'm going to use this version of R this time. Again, use whichever one you want based on what units you want to cancel out. So multiplied by 8.31 joules per mole Kelvin. And delta T, which in this case is T2, which is 450K, minus T1, which is 300K. Okay? And if I plug that in the calculator, I will find that work from state 1 to state 2 is equal to 405 joules. Okay? Actually, I'll use red ink because that's one of our final answers for part B. All right. Now let's find Q12, or the heat transfer from state 1 to state 2. So Q12 will be equal to, remember it's an isobaric process, and for all isobaric processes, the value for Q is, let me get rid of that. The value for Q is NCP, or the molar heat capacity for constant pressure, times delta T, which is a change in temperature, okay? This is only true for constant pressure or isobaric process, okay? Anyways, before we go further, we don't know what CP is. We weren't given the value for the molar heat capacity for constant pressure. But I know we're dealing with a diatomic gas, right? It's stated in the problem the cylinder contains oxygen. Oxygen, O2, is a diatomic gas. So, and it's ideal. So, we can say that we know that the ratio for molar heat capacity is equal to Cp over Cv, right? And I know that for a diatomic gas, Cv is equal to 5 over 2R, okay? For diatomic gas. So then instead of writing Cp, I'm going to say Cp is equal to gamma over Cv, right? So what else do I know? I know that for a diatomic gas, gamma equals 1.40, right? That's the value of the ratio of molar heat capacity for a diatomic gas. And if you don't know that, you should have these in your cheat sheet or memorize it because you need it. But you'll find it in the book. Okay, so back to our problem. So instead of Cp, I'm going to say N multiplied by gamma Cv, right? The ratio of molar heat capacity times molar heat capacity for constant volume times delta T, okay? So N is equal to 0.325 moles. Gamma is equal to 1.40. Cv is equal to 5 over 2R, or 5 over 2 multiplied by R, and in this case, I'm going to use this value of R, 8.31 joules per mole Kelvin. Multiplied by the change in temperature, which in this case, again, is 450 K minus 300 Kelvin. Okay, and we're going to find that the heat transfer from state 1 to state 2 is equal to positive 1,417.89 joules. All right, so that is for our, that's our heat transfer, our Q. All right, now let's look at the process from state 2 to state 3, right? And that is, again, an isochoric process where volume remained constant. If work is the area under the curve, and in an isochoric process like we have from state 2 to state 3, there's no area because we have a vertical line, right? Because it remains at 6 liters. Then work will be equal to 0. And it will be the same for the process from state 4 to state 1, right? It remains 4 liters, so there's no area underneath that vertical line. Okay, so we'll say isochoric process, therefore the work between state 2 to state 3 is equal to 0. All right, that makes it very easy. Now let's find our heat transfer. So to find the heat transfer, I'm going to use the first law of thermodynamics. Change in thermal pressure is equal to heat transfer minus work done by the system. Okay? Again, I'm going to cancel out work done by the system because I know for an isochoric process that value is 0. Therefore, my heat transfer from state 2 to state 3 is going to be equal to the change in thermal temperature from state 2 to state 3. All right? And remember, for all processes, delta ETH, or the change in thermal energy, is equal to N CV delta T, right? So this is equal to delta ETH for any process, isochoric, isobaric, or isothermal. Okay? So let's plug our values in. We know that the value for N is 0.325 moles. Oops, don't forget the units. CV is 5 over 2R, right? Because it's a diatomic gas. And for R, I'm going to use 8.31 joules per mole times Kelvin. And the change in temperature is from state 2 to state 3. That goes from 250 Kelvin. That's the temperature at state 3 minus the temperature at state 2, which is 450 Kelvin. So then our heat transfer from state 2 to 3, if you plug that in the calculator and cancel out units, will be equal to negative 1,350.37 joules. Okay. Nice. We're getting closer. So now let's go to state 3 to state 4. So state 3 to state 4, which is now we're dealing with an isothermal process. Okay? Again, I'm going to use my first law of thermodynamics. Change in thermal energy is equal to heat transfer minus work done by the system. So it's isothermal, so there's no change in temperature. Therefore, there's no change in thermal energy and internal energy, right? Thermal energy is the same thing as internal energy, right? For our case. So then we'll say that heat transfer, Q, is equal to work done by the system. Okay? Now, let's recall for isothermal processes, work done by the system is equal to N times R times T times the natural log of V2 over V1, right? By the way, V2 over V1, that just means final volume over initial volume for the state. So in our case, that will be V4 over V3, since we're going from state 3 to state 4, okay? Okay, so let's find that. So then our heat transfer from state 3 to state 4 is going to be equal to the work done by the system from state 3 to state 4. Right? I'm just going to call that work 3, 4 to simplify it. And then moles, N, we already discussed, 0.325 moles. R, again, I'm going to use 8.31 joules per mole Kelvin, so I could cancel out those units and be left with joules. The temperature, what is the constant temperature from state 3 to state 4? It said that the temperature remained constant at 250 Kelvin. Okay? That was given here in the problem. That was given in the problem. All right, state 3, 250 Kelvin. Okay. And then times the natural log of not V2 over V1, but what's the final volume in this process? It's V4. And then where did we start? We started from state 3, so V3, volume at state 3. Okay? Actually, I'm going to plug in those values. So what is my volume for at state 4? At state 4, my volume was 4 liters. And at state 3, my volume was 6 liters. Okay, so let's plug that in the calculator and cancel out the units. We find that the heat transfer from state 3 to 4 is equal to the work by the system from state 3 to 4, and that is equal to negative 237.76 joules. Okay, so in one go, we were able to find heat transfer and work, which is nice because it saves us time. So now let's go back to state 1. So we're going to go from state 4 back to state 1 to complete the cycle. And remember that is isochoric, right? That was that vertical line in the PV diagram right here. So what do we know about that? If it's isochoric, there's no area underneath that vertical curve, right? That vertical line. So work, right away, we already know. Work from state 4 to state 1 is equal to 0. No need to solve that. Because isochoric, right? Constant volume. All isochoric processes have 0 value for work. So work is 0 for all isochoric process. All right, now let's use again our first law of thermodynamics. Change in thermal energy is equal to heat transfer minus work done by the system. I'll cancel out work done by the system since it's isochoric and we know its value is 0. So then Q is equal to delta ETH, right? Which we said earlier, for all processes, the change in thermal energy is equal to the number of moles times the molar heat capacity for constant volume, or capital C subscript V, times the change in temperature, right? So let's just plug that in. 0.325 moles times, again, for a diatomic gas, CV is equal to 5/2 times the constant R. Okay? So 5/2, and then the constant R is 8.31 joules per mole times Kelvin times my change in temperature, which is my temperature at state 1 is 300 Kelvin, because that's where we go. That's our ending destination. And our starting destination in this process, we subtract it by 250 Kelvin. Okay? So this is T1 and this is T4, right? Because we go from state 4 to state 1. All right, so that was our Q41, right? So then if you plug that in the calculator, you would find that the heat transfer from state 4 to state 1 is equal to positive 334.40 joules. There you go. Oh, real quick. Sorry, I didn't see this because I was looking at my cheat sheet. We weren't given what, not cheat sheet, but I had solved this problem before recording this. So we weren't given T4 actually. So we have to do a side mission, right? So if I erase this, so we know what T1 is, but we don't know what is the value for T4, okay? So we have to do another side mission to get that. Okay, so side mission, we use brown pen. Okay, so side mission number 2. So we're going to use the ideal gas law, PV equals nRT, to solve for temperature at state 4. So temperature at state 4 will be equal to pressure at state 4 times volume at state 4 divided by N and R, the constants N and R. So We already know the pressure at state 4, that's 1.67 atm. The volume at state 4 is 4 liters, divided by the number of moles, which we solved for earlier, it's 0.325 moles, times R, which, since I have ATM in liters, I'm going to use the version of R that has liters and ATM in the denominator. So that's 0.08206 liters times ATM over mole times Kelvin. Okay? And if I plug that in the calculator and cancel out my units, I would find that I would have a temperature at state 4 of 250.47 Kelvin. Okay, that's my temperature at state 4. So now I can plug that in here, and delta T, right? My final temperature minus initial temperature. So since we go from state 4 to state 1, my final temperature is T1, and my initial temperature is T4, or 250.47 Kelvin, okay? And then when you plug that in your calculator, then we will get that the heat transfer from state 4 to state 1 is equal to 334.40 joules. Okay, there you go. And I think we are done with part B. Okay, so now let's move on to part C. And part C, it is said to calculate the net work or the total work done by the oxygen in the complete cycle. Okay. So net work is the same thing as total work. So that's what we're looking for, right? And the total work is just going to be equal to the work in each process. So work from state 1 to state 2 plus work from state 2 to state 3 plus work from state 3 to state 4. And then to round it back to state 1, work from state 4 to state 1, right? That's just looking at the PV diagram. So we have a work from state 1 to state 2 plus the work from state 2 to state 3 plus the work from state 3 to state 4. Sorry, that should go the other way. So plus the work done from state 3 to state 4. Then back to square 1, so the work from state 4 to state 1. Okay. So we'll just add our work that we solved for, right? Work from state 1 to state 2, work from state 2 to state 3, work from state 3 to state 4, and work from state 4 to state 1. Okay. All right, so I'll plug in those values here. So we found that the work from state 1 to state 2 was 405 joules plus 0 because there's no work done in an isochoric process, right? Which is what we had in state 2 to state 3. Plus work from state 3 to state 4, we found that to be negative 273.76 joules. Plus the work done from state 4 to state 1, again, that was an isochoric process or constant volume, so there was no work. So the value is 0. If you plug that in your calculator, you'll find that the total or net work is equal to 131.24 joules. All right, so that is our answer for part C. All right, we're getting there. We're almost at the end of the road. Finally, for part D, we were asked to find the efficiency of this device as a heat engine, right? Efficiency of the device as heat engine, and compare it to the efficiency of a Carnot cycle engine operating between the same minimum and maximum temperature of 250 Kelvin and 450 Kelvin. Okay? All right, so let me move part D a little bit. Okay, part D, find the efficiency, right? And then compare the efficiency with the Carnot efficiency. Okay? That's our tasks for part D. Let's start with the efficiency of the heat engine. The efficiency of a heat engine is equal to work out over QH, okay? Which is a heat transfer from the hot reservoir, right? Or for a heat engine, that would be the heat that enters the system, right? By the way, work out, this is the work done per cycle by the heat engine. Which we calculated earlier, right? That's work total. So then the efficiency would be equal to the work, which we calculated earlier as 131.24 joules, divided by, what is the heat transfer from the heat reservoir that entered our system? That would be all positive values of Q, right? So let's go to Q12. This is positive, so we're going to add that. Q23, that's negative right here, so I'm not going to add that. Q34, that's also negative, so that's heat leaving the system. I'm not going to add that. This is the heat transfer from state 4 to state 1 is also positive, so I will also add that. All right? Okay, so that would be plus. So basically this was the work total over Q12 plus Q41, right? I believe that was 12. Yeah. Which is, Q12 was 1,417.89 joules, plus Q from 4 to 1, which was 334.40 joules, okay? Plugging that in the calculator and canceling out your units, you'd find that the efficiency is equal to 0.0749 or 7.49% efficiency for our heat engine in the problem, okay? So now let's compare it to the Carnot efficiency. The formula for Carnot efficiency is equal to 1 minus Tc, which is the temperature of the cold reservoir, versus Th, which is the temperature of the hot reservoir. And I believe that was given to us here in the problem, with a minimum and maximum temperature of 250K and 450K for the Carnot cycle engine, okay? So let's plug those values in. 1 minus 250K over 450K. That's a maximum temperature and the minimum temperature, right? And if you plug that in your calculator, again, cancel out the units, you would find that the Carnot efficiency for the same heat engine, or for the heat engine with the same minimum and maximum temperature, is equal to 0.444 or 44.4% efficiency. right? Now, if we compare our efficiency of our heat engine and the Carnot efficiency of an engine, the Carnot cycle engine, with the same minimum and maximum temperature, by comparison, the Carnot efficiency is much more efficient, right? Because we can see that we went from 7.49% efficiency to 44.4% efficiency with a Carnot efficiency. So kind of a long problem, but hopefully that was fairly clear, and hope that